Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we're going to learn about linked lists. With linked lists, we diverge from the highly structured linear data structures like arrays. We know arrays are indexed, we know their length, and all the items must be continuous in memory. On the other hand, linked lists are a very loose data structure. We don't maintain index or any of those details, we don't know the length, and the items aren't required to be next to each other in memory. However, it's worth noting that linked lists are still linear. There's a starting point and an ending point, and then one single path to go from the beginning to the end. Later in the course, we'll start to explore non-linear data structures like trees and graphs, but they will have a lot of similarities with linked lists, so a lot of concepts you do learn in this lesson will then be transferred to more complex data structures. As with any data structure, there are trade-offs. We lose the structure of arrays, but with linked lists, we gain more flexibility. Each item in the linked list is its own object, and we call these items nodes. Each node is going to contain a data attribute, which is just the value that this node is going to contain. So very often in interviews, they're just integers, but it can be any data type. The other attribute that's required is a next pointer, and this is the only way to get to the next item in the linked list. So we start at the head, or there's a variable that stores the head node, and then to iterate through it, we just go to item.next. And then once we reach this item, we call .next again. And by continuing to do this, this is how we iterate through each item or node in the list. And then we're at the end when we reach the tail. And we know we're at the tail when its next pointer points to null. So we can think of a linked list as if each node were its own bucket. And this bucket is going to contain some data inside of it. Then we're connected to the other buckets through the next pointer. Or we have this chain that connects them all. So each bucket is its own individual item, with this chain just simply connecting them. And the only way to get access to the list is through the head pointer. So you must start from the first node every time and then iterate through. And then you can only go through each item by going to its next pointer. Optionally, you may have access to the tail, but this is going to be determined by the interview prompt. Another good analogy for linked lists are trains. Each train car is going to have its own payload, or the data of that node, and then we only are connected to the node in front or behind it through its coupling. So each individual car only has knowledge of itself and its neighbor, but not the train as a whole. And then if you started at the front of the train, the only way to get to the car you want is just walk down each one. So up to this point, we've only been talking about singly linked lists, where there's a node and a next pointer that points to the item after it. Then we can only move in one direction, so you can start at the beginning, and then walk from the beginning to the end by following its next item. But then there are also doubly linked lists that have a next and a previous pointer. So you can move in two directions. You can go to the item after the current one, or the item before the current one. So with the head node, its prev is going to point to null, and the tail node, its next pointer is going to point to null, and then every other item in the list is going to point to the one after it and before it with a next and prev pointer. So the main difference here is singly linked lists can only go in one direction. So if you reach a node and realize you need to be at an earlier spot in the list, so the only way to get back to it is to then start over at the head node again and then iterate forward. However, with the doubly linked list, you can move in either direction. So you can go forward in the list, or if you need to go backwards, you just follow the prev pointers. So both singly linked lists and doubly linked lists can only move one item at a time. The only difference is that singly linked lists can go in one direction, but doubly linked lists can go in both directions. So if we looked at a singly linked list in code, it just has this data property, or the value stored in the node, and then the next pointer, which points to the next item in the list. With the doubly linked list, it has the data property and the next pointer, but then it also has this previous pointer, which is the reference to the previous item. So in interviews, by far the most common way to be given the list is just to be given a head node. So you just have one item, and then you're forced to iterate through every item in the list to solve the problem. It's optional that you could have a doubly linked list, where you also have a prev pointer, but it's much more common to just have a singly linked list where the input to the question is just the head node. If we were to use a linked list in real life, it's possible you could have this wrapper object, which maintains a reference to the head pointer, and possibly the tail, but then gives you other functions and methods to interact with the linked list. But in interviews, it's very unlikely to be given this. You will almost always just be given a head node. So let's quickly compare linked lists and arrays again. With arrays, they're stored contiguously in memory, so each item is indexed and we know the full length. So at each memory address, we have a character for hello. So each item just appears one after the other in memory. However, a linked list can appear anywhere in memory. All it does is point to the other item or tell you where in memory to find that item. So we have H at slot 321, and then it points to E at slot 981. So in this first item's node, it simply tells you the memory address of the second item. And then this item's next pointer tells you where the other one is, which is once again in a totally random and not connected memory address. And then finally, when we get to the end, the next pointer of the last item points to null, indicating we're at the end of the linked list. So with linked lists, the big O for the lookup is O of n linear time because you must walk through every item to find the one that you're looking for. If we want to append an item, it's going to take constant time if we have a reference to the tail, because all we have to do is update its next pointer. If we don't have a tail, we must iterate from the head to find the tail and then add that last item. It's constant time to prepend a node because all we have to do is add this node in front of the current head, so we're only updating one pointer. To insert an item, it's going to take O of n linear time because we have to walk from the beginning to the spot that we want to add the item. To delete an item, it's going to be the same. We have to walk from the beginning and find the item that we want to delete. And finally, it's going to take O of n linear space because we must store n nodes. So the real important takeaway with the big O complexity is that when we have a pointer or a reference, we can operate in O of 1 constant time. So since we maintain a reference to the head, we can add an item before the head in constant time. And if we have a tail, it's constant time as well. We just have to update one value without any iteration. So it's also possible if you want to have fast operations at any other point in the linked list, you can just maintain more pointers. Anytime you update a pointer or a reference to another node, it's always constant time. So the pros of a linked list have to do with how loose and flexible it is. With a linked list, it's flexible size and data can exist anywhere in memory. And in fact, it can be distributed. All you have to know is where to find the next item from the current node. Even though a linked list is a loose data structure, it's still ordered. It's always going to follow the same next pointers to get from the beginning to the end, so it's still a great choice for this linear ordered state. And finally, you get fast operations when you have pointers. So if you have access to a pointer and don't need to iterate, it's always going to be constant time. The downside to linked lists is that we have slow lookups. We don't maintain keys or indexes that allow us to access items. So if we do want to reach a specific item, we must iterate from the head and get there in O of n linear time. This also means that if we want to insert or delete at this item, This will also then degrade to O of n linear time because we had to iterate there. We only get that constant time, insert and delete, if we already have access to a pointer at that location. So now the question is, when and why would we want to use a linked list? Maybe the most common example is the back and forward button in the browsers. All we care about is the previous and next item that we were looking at, so it just maintains a pointer to the current page, and then you can go forward by calling the next item in the list, or you can go backwards by calling the prev item. So the back and forward button in a browser can operate as a doubly linked list. Linked lists are also very low-level data structures, and we often use them to implement other data structures. So stacks and queues, they want fast operations at the end, which is very much in line with the head and tail pointer, so you can implement stacks and queues very easily using a linked list. And in fact, we do that in this course. Blockchain technology is becoming very, very popular, and the core fundamentals of it follow linked lists. We have these distributed nodes that each hold data and point to the previous and possibly next item in the blockchain. And finally, the undo button in our text editors functions like a linked list. It's very similar to a back and forward button in a browser, where it just remembers the previous state and you can walk backwards or undo and follow each one to the next version. So the pattern for all of these is that we simply maintain a reference to the item before or after the current one that we're looking at. So for interviews, what you need to know for linked lists is 1. Be comfortable taking an input of a head node for a singly linked list and iterating from there. Another is the runner technique. This is a very commonly used pattern in linked list interview questions. Another important concept is using multiple pointers in your solution. So in addition to the head and possibly the tail, you'll need to maintain pointers to other items in the list to keep getting those fast operations at other locations. And finally, just know the different linked list techniques and operations. And now quickly to follow up on the runner technique, you'll use this in the course, but I want to briefly mention it here as an introduction. And really the key to it is that when you iterate through the linked list, instead of just using one pointer, you have 2 or more pointers. You have a lead pointer that goes out first, and then a follow pointer. And this can be done in a few different ways. One is to iterate the lead pointer a number of spots ahead of the follow pointer, and then move them both simultaneously, one node at a time. Another possibility is that you start the lead and the follow at the same time, but then for the lead, you iterate 2 spots for each 1 spot of the follow pointer. And now let's tackle some linked list interview questions. Thanks everyone, and I'll see you in the next lesson.